Today, we're going to look at different weather instruments that are used in the industry. Now, the first thing that we're going to look at is more of a weather station, and this is called the Stevenson screen. Now, the Stevenson screen is just a wooden box that stands on four legs at a height of approximately 121 centimeters. Now, this is to avoid the ground heat affecting the thermometer bulbs that are in the box at 125 centimeters. Now, remember, as the sun is shining, it's giving off heat. Some of this heat can be reflected by clouds or absorbed by air molecules, and a lot is absorbed by the ground. The ground will then redistribute and radiate this heat into the atmosphere. If this box was on the ground, this heat would affect the thermometers and the temperature readings would then be inaccurate. Now, the Stevenson screens are also painted white, and this is to reflect the sun's rays, also to make sure that they do not heat up. They are made up of wood to prevent heat transfer, as wood is a good insulator. And the sides are slated to allow free movement of air. This also keeps the box pretty cool. Now, the wood also is double layered with an air space in between, which also helps for insulation. Then the screen is also placed on grass, and this also reduces the ground heat. So you can see in the image above that there's grass at the bottom of the Stevenson screen. Now, the Stevenson screen is used to house different data. Now, on the outside of the Stevenson screen, we can get things like a rain gauge, a wind vane, and an anemometer. Now, it's very important that the rain gauge must be in an open space, twice its height from the nearest object. The wind vanes and the anemometers should be placed outside, away from trees, buildings, or any obstacle, and at least 3 times the height of the nearest obstacle, so that nothing interferes with the data that it collects. Then on the inside of the Stevenson screen, we might have things like a maximum minimum thermometer, which is also called a 6's thermometer, and a hygrometer with a wet and dry bulb. Now, usually daily readings are taken at the same time. This is to make sure that the readings are constant and the data do not have any other variables. Your readings will differ immensely if you take a reading the first day in the morning, the second day 12 o'clock in the afternoon, and the third day in the middle of the night. Then they won't be reliable. So, in today's world, meteorological stations send data to the Met Office's computers using automated digital recording equipment. This is much better than taking readings every day at the same time, as you'd need less manpower, there's no human error involved, and continuous readings can be taken by the equipment and sent to the computers. Let's have a look at these equipment in a bit more detail. So the first one we have is a wind vane. And a wind vane is used to measure the direction of the wind. Now, the direction of the wind is measured from where the wind is blowing in terms of compass direction. So this would be things like south, north, or northeast, which means that the unit of measurement of the wind direction is the same as a compass direction. Next, we have an anemometer. Now, this measures wind speed. Now, the wind speed is measured in meters per second or kilometers per hour. So it's the same as measuring the speed that a car goes. Now, the anemometer has 3 or 4 cups on metal arms that spin freely on a 10-meter vertical shaft. So here is the cups and here is the shaft. We can also see in the image above that they have included a wind vane. So the cups will rotate and the counter will record more rotations with stronger winds and less rotations with weaker or slower winds. Now we also get digital portable anemometers that you can hold in the wind. The fan that's included will then revolve to display a number on the screen that you can record as the wind speed. Now, many digital anemometers send data directly to apps and computers for readings. Now, both wind vanes and anemometers need to be very far from buildings and trees and other obstacles that could block airflow. Buildings can also form wind tunnels or delay airflow. This would alter your readings, and your readings would be incorrect and unreliable. We can then move to precipitation, which is measured through the use of a rain gauge. Now, precipitation is any water that falls to earth. So this can be rain, it could be hail, it could be mist, it could be sleet, and it can even be snow. Now, the unit that we use to measure rainfall or precipitation is in millimeters. As with wind, at the same time each day, any water that has collected is poured onto a tapered measuring cylinder, which is laid on a flat surface. The water level is then read with the eye at the same level as the lowest part of the meniscus of the water. This is very important, as if you are standing above the waterline or below the waterline, inaccurate measurements will be taken. These measurements are then recorded, and if it's too small of a reading, maybe because of mist, then we say that it's recorded as trace water. So not enough to even have a millimeter reading. Now, when it comes to rain gauges, the same with wind equipment, they need to be placed away from buildings and other obstacles. This is because trees, buildings, and obstacles will obstruct rainfall, and an inaccurate measurement will be taken. We can then also measure temperature. Now, temperature is measured in the units degrees Celsius or degrees Fahrenheit, and this depends on the location. We know that in South Africa, we use degrees Celsius. Now, usually when we measure temperature, we measure the shade temperature. This is because the temperature will be variable in direct sunlight. The temperature can also be affected by cloud cover and insolation. Now, when temperature is taken, we usually take the daily minimum temperature as well as the daily maximum temperature. We can then work out the average temperature. So we can do this by taking the maximum temperature, adding it to the minimum temperature, and dividing it by 2, which would give us the mean daily temperature. Now, the temperature range across 24 hours is called the diurnal temperature range. Another thing that we can do is we can record the daily mean temperature for a month and then divide it by the number of days in that month, which will then provide us the mean monthly temperature. And then if we take the sum of the mean monthly temperature and divide it by 12, it will give us the mean annual temperature. Now, temperature can be measured by using a traditional 6's thermometer, which houses a maximum and a minimum thermometer, kind of in a U shape. We can then also use a thermograph. Now, a thermograph has an exposed bimetallic strips, which can then deform with a change in the temperature. Now, this change is then transmitted to amplify levelers, which trace a curve on a roll of graph paper. So the vertical movement of 1 millimeter by this lever is equivalent to approximately 1 degrees Celsius. We then also get a piece of equipment called a wet-dry bulb thermometer. Now, the dry bulb thermometer measures the ambient air temperature, but the wet bulb thermometer has a wet cloth or wick wrapped around the bulb. So as the water from the cloth evaporates, it cools the thermometer, causing it to read lower than the dry bulb, unless, of course, the air is fully saturated. Now, the wet dry bulb thermometer is a simple device and can be used to measure the relative humidity as well as the dew point. Humidity can then also be measured by hygrometers, and just like wet dry bulb thermometers, it measures the relative humidity. Now, relative humidity is the measure of the amount of water vapor in the air compared to its maximum capacity at any given temperature. Now, the basics are that warm air holds more water vapor than cold air. So when the air is holding as much moisture as it can, it is said to be saturated. Then we need to be able to measure air pressure. Now, air has weight and it exerts a pressure on the Earth's surface. Now, sea level pressure is approximately 1.03 kilograms per centimeter squared. Now, the pressure will vary with altitude but also with temperature. Now, the unit that we use to measure the pressure is millibars. Now, we use a barometer to measure air pressure. So there's 3 different types. The first one is a mercury barometer, and it's a hollow tube with all the air being extracted from the tube. So the open end is then placed in a bath of mercury. The atmospheric pressure on the mercury in the bath will force it up the tube. So when the tube pressures equalize, that's the pressure on the outside of the tube and on the inside of the tube, the mercury will stop rising in the tube. The height of the column of mercury will change as the air pressure changes. So this column will rise as the pressure increases, and it will fall or drop as the pressure falls. We then have an aneroid barometer, and it has a partly vacuumed, corrugated metal chamber inside. So there's a strong metal spring within the chamber that prevents it from collapsing. The spring will expand and contract with the changes in the atmospheric pressure. The levers will magnify these changes as these changes are very minuscule, and a pointer will then move across a calibrated scale to show the atmospheric pressure at that given time. Lastly, we have a barograph, and this is a continuous reading of atmospheric pressure for 1 week. So a barograph has a flexible arm that tracks changes in pressure on a rotating cylinder. So paper with 2-hour vertical lines divide across it and covers the cylinder. This is very similar to the equipment that we use in temperature changes as well. Now, to illustrate pressure changes, we can use a map. Now, the lines of the different pressure on a map is called isobars. Lastly, we're going to look at sunshine hours and cloud cover. Now, with sunshine hours, we use a Campbell-Stokes sphere that calculates the hours and minutes of sunshine that a location receives. Now, the recorder is a metal-framed glass sphere. The sphere focuses sunlight on a recording card below the focal point. The rays will then leave a trace on the card, indicating the length of the sunshine at that point. At a day's end, the card is then replaced. The card cannot be reused as it's a permanent burn that is inflicted on it by the sun. Now, a sunshine recorder is first placed in an open space, usually south-facing in a northern hemisphere or north-facing in the southern hemisphere. So we will use a north-facing sunshine recorder. We then have to make sure that the recorder is outside and unaffected by shade and has direct exposure to the sun's rays. So it needs to be away from buildings. You can maybe put it on the roof of a building. It could be on a pedestal or a stand. It should not be close to any trees or any other obstacles that can get in the way of the rays of sunlight. Lastly, we have cloud cover, and cloud cover is measured in units of octas. Now, each octa represents an eighth of the sky that is cloud covered. So 0 octas means a clear sky, and 8 octas a total coverage. Now let's look at this example of the clouds. So if we should draw lines on this image to show 8 parts, see that about 1, 2, 3, 4, 5 of the parts of the octa is almost fully covered. So this cloud cover would be 5 octas. Here we have another example, and in this example we do not even have to draw our lines. We can already see that this would be 8 octas as its full cloud cover. So one more example, here we can see that this is about half an octa, 1, 2, 3, 4 octas of clouds.